Today, we're going to look at some beautiful visuals. Hey everyone, Tino here. Welcome back to the channel. So, going to do a slightly different episode today. We're actually going to look at a website that one of my friends recommended I check out. It's supposed to be visual statistic. You know, I love it. Makes the learning experience much easier and it just makes a lot more sense. So, I'm going to check it out live and direct with you, and let's see what it's all about. As always, you know what to do. Like, subscribe. I mean, it helps me, helps other people that enjoy this find it as well. And thank you to all the recent subscribers. My numbers have been going through the roof, which is really awesome. So thank you all, and love the comments as well. You know, I love the encouragement. There's really no trolls at all in the comments, which I'm sort of surprised. Maybe I'm not popular enough. So maybe I need more trolls. That will make me popular, keep the arguments going. You know, Bayesian versus frequentist. I don't know. I got to sort of bring up some controversial stuff, and you know, they'll come flocking. All right, let's have a quick look. So it's apparently called seeing theory. So let's have a look. Seeing theory. All right, let's have a looky. Supposed to be this one here. All right, now this is nice. I really like how these little circles behind sort of tend to react to my mouse. I mean, that in itself, I could just play around with this. I mean, there's quite a lot going on just for that. So this is seeing theory. Obviously, I won't bore you with the little balls. You can play it in your own free time. But look, a visual introduction to probability and statistics sounds right up my alley. Brown.edu, so I'm guessing it's from Brown University. I don't really know much else. We'll have a look at the about. I mean, you know, have a quick look at the about. All right, so you got these 4 people over here. Undergraduate. Okay, let's have a quick look. Let's go home and let's start. What are we seeing? Basic probability. So this chapter is an introduction to the basic concepts of probability. So apparently the basic concepts are chance events, expectation, and variance. Okay, let's have a look what happens. I'm going to click that. Chance events. Randomness is all around us. I love it. I love abstract concept like that. And I think it is. It is. Life is all about randomness. Obviously, some believe in that stochastic process. Some don't. Some think it's deterministic. Your path has already been set. Where do I sit? I don't really know. I think... I don't know. Maybe for another video. Probability theory is the mathematical framework that allows us to analyze chance events in a logically sound manner. Can't disagree with that. The probability of an event is a number indicating how likely that event will occur. This number is always between 0 and 1, where 0 indicates impossibility and 1 indicates certainty. Pause. I sort of agree with that. I think in games or events that can be repeated, such, you know, dice throws and that sort of stuff, I think that number does make sense. You know, that repeatability has an implied meaning where, you know, repeated sampling, this is sort of what the distribution I expected to see. I think for single events, and what do I mean by that? I mean by presidential election. I mean by... things that you can only do once. You cannot repeat this time and time again. I think the probability is either 0 or 1, probably at the same time, and see that's the outcome. It's not I can repeat it and it's like 55% chance. 55% chance means that if I run it 100 times, 55 out of those 100 times it's going to come out, you know, winning, positive, true, whatever that means. But for events that are not repeatable, I don't quite like associating a probability. You might have... Anyway, that's my little opinion there. Going on a tangent, which, you know, I love a bit of trigonometry. Classic example, probability, fair coin toss. 2 possible outcomes, heads or tails. Obviously pretty straightforward. In this case, probability of flipping your head is half. Actual series of coin tosses, we may get more or less. So obviously, that's a little bit of variance happens there. As the number of flips increases, the long-run frequency of heads is bound to get closer and closer to 50%. Obviously, you imagine them to convert. So we've got H here. I'm guessing that's head. For an unfair or weighted coin, the 2 outcomes are not likely. You can change the weight distribution of the coin by dragging the true probability bars Okay, so we got these 50-50. Can I drag? Very, very nice. Let's make them 50. Okay, what if I flip the coin? So flip the coin once, it came out tails, 100%. So, one time. That's what I was sort of talking about. You can only do this event once. It's either 100% or 0, right? If I flip it again, all right, came out tails. Flip it again. Came out head. So I had 2 tails, 1 head, a third, 2 thirds. Let's flip it 100 times. It's starting to stabilize another 100 times. 100 times, 100 times, 100 times. Let's keep jamming it. Starting to approach 50-50. What if we starting to make this unbiased? Flip the coin. I'm expecting more heads than more tails. Flip it 100 times. It should obviously approximate this on the right. I mean, that's cool. It's a chance event. Pretty nice. I like the graph. I like that you can interact with it. I think that's really nice. I mean, good simple graphics. Great. Expectation. Expectation of random variables number that attempts to capture the center of that random's variable can be interpreted as a long-run average. So I guess that's sort of like the sample mean given the distribution. More precisely, it's defined as a probability-weighted sum of all possible values in the random event support. Obviously, you've got all these different possibilities. Like, I guess here we've got a dice. You've got like a 6. The weight is like a 6. What is the essentially expected value for that? So if I multiply 1 by 6, 2 by 6, and so on and so forth, obviously that's the expectation's 3.5. There's no 3.5 on the dice. They're obviously all integers, right? But that's still sort of that expected value. If I roll the dice once, what value do I get? I had a 6. Expectation's 3.5, and then if I just keep rolling, I'm gonna roll it 100 times. It should converge to that blue line. I'm actually surprised it's actually quite a bit lower. I mean, that's 3 and a bit. I mean, I can adjust them down here. Oh yeah, so I can actually change the weights, and that's pretty cool. You can change the weights, and that changes the expected value in real time. So if your dice is loaded dice, if you're playing against some cheaters, what do you expect the dice to be? Beautiful. So that's the sort of thing at the casino. It is, you ideally want to be in this sort of part of the distribution, because long term the house has the advantage, right? The probabilities are going to converge, and they have the upper hand. So in the short term, yes, variance can be in your favor. You can win at roulette, blackjack, whatever it might be, right? But as you play hundreds and hundreds of hands, they have a slight advantage, and that's where they get you. This is cool as well. Simple, straightforward. It's a loaded dice. What's the expected? Right, let's keep going. Variance. All right, so this is starting to get sort of a slightly different, slightly more advanced concepts here. So whereas expectations provides a measure of centrality, the variance is a random variable quantifying the spread of that random variable's distribution. So that I was saying, like, what are the sort of possible values, and how spread out are they? The variance is the average value of the squared difference between the random variable and its expectation. So sounds more complex than it is, but essentially it's taking that expected value, the squared difference between the random variable and its expectation. Expectation is what we did before, and then the actual value itself, and then you sort of square it. So it gives you this cube. This square, right? Not cube. That would be sort of 3-dimensional. Draw cards randomly from a deck of 10 cards. As you continue drawing cards, observe that the running average of squared differences in green begins to resemble the true variance. All right. Okay. So if I draw a card, I drew a 5. Goes there. I'm going to draw another card. It's another 5. Wow, what's the chance of that? An 8. I'm going to draw another one. I'm going to draw it 100 times. Eventually, should resemble that another 100 times. Actually, quite surprising how, even though doing this like 1,000 times, not actually converging, which is really quite odd. So what can I do here? I can exclude the cards. So that's my expected value, 8. Right, if I draw, my variance is 2, because obviously there's less possibility. There's less possibilities, right? As I have less and less cards, if I just have 9 and 10, the average is like 9.5, right? But obviously the variance is going to be tiny because I can only draw 9 and 10. If I include a 1, that expected variance now is going to become massive, even bigger. 1 and 10, you could either get one of those two. Average between 1 and 10, 5 sits here. So let's just draw that. That should be huge. Okay. So it actually seems like the convergence is dependent on how many cards I have, and actually even drawing 100 samples, 200 samples, it doesn't quite converge. So it looks like something might be off unless I'm missing something. I'd expect it to be quite close to 8.25. Anyway, that was nice. Pretty straightforward. I like that you can play around with them, and becomes very visual. Let's go to the next one. Compound probability. All right. Okay, so this chapter discusses further concepts that lie at the core of probability theory. Okay, set theory. We will love a bit of set theory. Being able to include and exclude things together. So this is sort of a typical, what do you call it, like a Venn diagram. So a set, broadly defined as a collection of objects, right? So, or A, B, and C. In the context of probability theory, we use set notation to specify compound events. So this event happening and that event happening, sort of interject onto one another, and you have that sort of overlapping, and that's going to be sort of your probability. We can present events as a roll of even number, say 2, 4, 6. That's your set. 2, 4, 6 would be my whole set. For this reason, it's important to be familiar with algebra, the algebra of sets. So that's just the notation of these sets, right? The beginning sort of can be quite confusing, but once you've got that shorthand sorted, it can become quite straightforward. So use the set constructor below to build a set, and then press submit. So A intersect of B. So that's both of them sort of the probability of these two events happening here. So this area here. A union B is either or, essentially. So you're adding actually these probabilities together. Obviously, you've got this full outer circle, which doesn't allow me to sort of have any more, but that's essentially your probabilities is the union. So we can do, what's this one here, complement. So a complement is like the not, essentially the inverse. So A complement essentially is everything but A. So we're excluding A. I guess you can add some brackets. So we can do open bracket A intersect B. So that should be this little bit in the middle. What if I do A intersect B complement? So it's everything but that little piece in the middle. I mean, that's cool. I mean, that's nice and visual. Once you get familiar with them, it's not really that many of them, it starts to make sense, right? So essentially, everything but the probability of these two things happening at the same time. So, it's pretty much sort of everything. Love it. Universal set, essentially everything. So it's just the U is like the everything. Right, this is pretty cool. All right. Don't really spend much time doing this sort of thing in real life, but it's still good to sort of get this sort of basic stuff counting. All right, so this is sort of permutations and combinations. Quite like this sort of stuff, right? So what have we got here? Surprisingly difficult to count number of sequences of sets satisfying certain conditions. For example, consider a bag of marbles in which each marble is a different color. If we draw marbles one at a time from the bag without replacement, so pretty straightforward, without replacements, you're literally putting your hand in the bag, taking them out, and it doesn't go back in the bag, right? So that's very important when you're talking about like sampling and bagging and bootstrapping, which I've got a great idea for a visual demonstration of bootstrapping, but that replacement or not, it really does matter. So how many different ordered sequences, permutations can these marble possibly make? So unordered sets, combinations. So choose how many marbles should contain. So if you've got 4 marbles, we could start with an A. How does this work? So first step, I can have 4 permutation. I can pick A, B, C on D. Second step, I can have 12, because it's saying, look, I can pick A from the bag. Right, I've got A, B, C, and D. What are my other possible steps? Let's just focus on this top one. You could potentially pick B. So your sequence would be AB. You could pick C, so your sequence would be AC. and then AD. And here the order matters. So AB is unique compared to sort of BA, hence why we've got 12. If we add another step, we've got less possibility. So A and B have already been drawn. Our only possibilities here are C and D, right? And obviously, if we go to 4, we exhaust everything. Essentially, every combination in every permutation has been picked, and there's essentially 24 here. I'm guessing with combinations, order doesn't matter. AB is the same as BA, and that's why we have less here, right? So we got A. Our possibilities is AB or AC or AD, but obviously it doesn't double up. You see, this B also has a path to up here. So actually pretty beautiful. And this is sort of like, I guess, like lottery numbers where they're not replacing, but the order doesn't matter in which like lottery numbers come out. So pretty cool. Obviously you can make it simple. Again, does it sort of matter? I guess for like really big permutations, combinations, can start to make some sense, but you know, good simple concept, quite visual. Can't move anything around. No. Next, condition. Wow. Make it rain. Look at that. That's beautiful. That's gorgeous. I really love like this visual concept, like this rain, these balls like raining down, and it seems that the initial random number has these black balls, and once it hits one of these bars, which is probably a probability, yeah, there you go, a third, they change color, right? So these black balls become orange. Here they become green, and here they become blue, right? And that's essentially your probabilities down here. It's like a third. That's pretty cool. So if I make that, what can I do? I can make that bigger. No, I can. Yes, I can change the size, and I can actually move it around, and that essentially changes these probabilities. Universe A, so everything starts with A. Conditional probability allows us to account for information we have about our system of interest. So they're already sort of passed through that. So hugely important conditional probability for Bayesian statistics, right? For example, we might observe the probability that it will rain tomorrow to be smaller than the probability that it will rain tomorrow, given that it is cloudy today. So that's sort of putting two pieces of information together, which help us actually create like a better picture of what might actually happen. So, you know, each one of these could be like an event, and what we could do is like essentially compound that event happening. So if we look at the colors down here, if you want to look at things that pass through A and B and sort of C, there will be far fewer, right? Pretty interesting. Mathematically, computing condition probability amounts to shrinking a sample space to a particular event. Obviously, the rain, I like to call it rain, these little balls, call it as you wish, they have to pass through that. So I'm sort of shrinking by that. So it has to hit A and sort of B. Obviously, we've made A huge. Oh, what have we done here? So in our rain example, instead of looking at how often it rains on any day, in general, we pretend that our sample space consists of only those days in which the previous day was cloudy, when we determine how many of those days were raining, right? So this is really nice. I love these visuals. I've always thought of using these, like, you know, shooting these little balls for like, you know, uniform random variables, or just, you know, random variables in general, and this sort of makes a lot of sense, right? This is clearly very uniform, and it's conditional on those. Beautiful, amazing work. Distributions, another thing close to my heart. Let's have a look. Random variables, discrete, continuous, and central limit theory. All right, let's have a look at this. Random variables. All right, so what do we do here? Formally, random variable is a function that assigns a real number to each outcome in the probability space. Define your own discrete random number for the uniform probability space on the right, and sample to find the empirical distribution. Okay. Value, I'm not really sure. Click and drag to select sections of probability space. Choose a real number and then press 2. Submit. 1. am I supposed to do here? Sample distribution. Ah, I've got these colors. Okay, that's starting to make sense. All right, so I've got these three colors: red, gray. This wasn't very clearly explained. Okay, red, gray, and blue. And I'm just going to keep shooting the background until I hit those colors. When I hit those colors, I'm going to mark somewhere what color it was, and that's going to be. So this is actually not a million miles from, I guess, MCMC. Like Markov chains, something like that, or that sort of sampling algorithms where you sort of observe something and then take the distribution, right? So obviously can I make more? I stop. So if I make this really big, that's my gray. And then, what have we done? Another color. Number 2, and this little one here is going to be number 3. If I sample from that, these two should be pretty similar. And obviously there's a lot of white because that's just the background. So no, this is really cool. This makes a lot of sense when you want to sample from a distribution but you don't know what the function is. This is exactly what you do, right? You just sort of measure something. You got loads of examples in terms of like measuring pi. So you have a circle when your little bullet comes, it's in the circle, out the circle, you mark it each way, and that you can actually measure areas and things which are don't have a closed form solution. So pretty cool. Like it. This is nice. This is really nice. Discrete and continuous. Two classes of probability distributions: discrete and continuous. What does that mean? So discrete is something that has like an integer, right? So units, right? 1, 2, 3, 4, 5, right? So you got probability of those. Select the distribution. All right, so let's go Bernoulli, pretty standard. And then here we have the probability. So with the Bernoulli, you have this value, this one parameter. It's a one parameter distribution, pretty easy. You have a parameter p, so it's either true or false. So Bernoulli random variable takes a value of 1, probability p. So we've set probability of it occurring is 27. So this down here would be 27, I'm guessing, yeah. And essentially 1 minus p, so not happening. The inverse is going to be 1 minus that, which is going to be what, like 83, right? And that's sort of pretty much it. Oh, okay. This is like a cumulative distribution function, I guess, is orange. All right, and that's should pop to 100. Done. Easy. All right. This binomial distribution have a mean and again a probability, and then you got this cumulative distribution function up and up and up. Right. Very straightforward. What about continuous? Obviously, in general, people are more familiar with when I say distribution. Usually, what do they think of? Standard, normal, right? Let's have a look at that. You've got a mean and a standard deviation value. I guess it's going to be the CDF. Follow it up all the way and all the way to 1. Beautiful. That's your cumulative distribution function. I like it. This is cool. This is really cool. Simple. It's not crazy graphics. Obviously, I love that rain and stuff, but this is sort of to try and understand a distribution. What's student T? I just standardized. So C here Z. I'm sure it's tiny on your screen, but Z N01. So distributed with normal distribution 0, 1, but it also has a K parameter, which is your nu or degrees of freedom. As it approaches above 20, I mean, it goes to infinity, it starts to resemble normal, and it has a limit of, well, shouldn't really go as low as 1, but I guess it's sort of some of the things are undefined. But yeah, so that's student T, something a little bit more like gamma. Yeah, gamma's cool. So I like it because it's sort of just positive. Gamma distribution, pretty nice. Beta, let's make it a little bit nicer shaped. Beta and gamma are sort of, I like to think of them as sort of twins. They've got these special characteristics. Yeah, nice. What else we got? Chi squared. Yeah. Never seen a CDF of chi-squared. Every day is a school day. Love it. Look, nice. Yeah, confidence intervals. I think that'll be very visual. You could do something very cool with this. Nice. Central limit theorem. As we keep drawing something, we should approach that sample mean. So let's just go sample. What did we do? Oh, we drew one value from the normal, from the uniform, and obviously it's going to average that. What if I draw? I'm going to keep drawing. Let's go sample size. Say 6. Draw 6. What's the average of those 6? It's this value here. I'm going to do another 6. It's going to be that. If I'm then going to do many draws, so 6 random numbers, average of that, and take the value. I'm going to do that, say, what's the max? 50 times. Oh, that's awesome. Look at that. We're starting to approach. So what's the theoretical is obviously going to be that normal. I wish that draw went higher than 50. I mean, maybe what if I make that bigger as well? How well does it fill that line? It's not bad, actually. That's pretty nice. Pretty nice. Here I can change my these parameters. What distribution is that at the top? It's like uniform, but interesting. Not sure. But yeah, that's cool. I really like this. Nice. That was a real big step up in terms of like the visuals. All right, frequentist inference. There we go. Here we're going to get the trolls and the haters. The Bayesians are going to come in and just throw mud. Point estimation. There you go. This is if this is going to do what I think it's going to do, yeah. Point estimation. We're going to throw darts, bullets, doesn't matter where you live, at this, and then take some sort of measurement to estimate pi. You know, what's the ones inside, outside, do a little calculation, off you go. So I'm going to go drop 1,000 samples. So just hit. You're going to see whether it falls in there or not. And then you start to get an approximate value of pi. I mean, you could do this to the trillions of times and then get a really good estimate of pi, but I'm sure there's a much better way. I'm not a pi scientist, but I'm sure they've got the ways and how they get to like have a millions of decimal places. Look, love it. Really like stuff like this. Pretty cool. Confidence interval, yeah. So this is around, instead of having like a point estimator, and like point estimator means that a lot of people, when they look at probabilities, make the mistake of saying, okay, what's the probability of someone being like 1.8 meters tall? It's like, well, if you want to be a pedant, which you know how I feel about those, it's actually 0. There's no probability that you're going to be exactly 180 point infinite like zeros, right, height, right? Most of the time you'd have to specify an interval. So between 179 and 181, right? You're going to get a probability of that happening, right? So this is what this does. Let's just look at normal. Makes everyone's life easier. So that's my mu. Contains mu, excludes mu. So actually, what happens here? We sample 5. We're going to sample there. Does it? You're going to have an average. Do we keep hitting the average? Yes or no? So that's my confidence interval. So, and what does that do? It's going to sample them wider. Yeah, so that's much wider, or my confidence interval around that point. Okay, so we're actually going to make those little winglets much higher. Yeah, obviously it's going to be much more likely that we're going to, essentially, does it include that number? So that's really what confidence interval, is. Most of the time you're testing whether a variable is 0 when you're like doing betas and t-tests on those. You're going, is 0 a valid number? As in, like, could this possibly 0? Because you're making a point estimate, but you're going, well, yes, it's like 1.7, but how likely is it that it's just 1.7? It's probably like I've got a bit of noise in my data. I'm not quite sure. So, well, is 1.6 a valid number? Well, probably, yeah. So how wide are we going to make this? If you include 0, it goes, oh, 0 is a valid number. Well, that variable is pointless, right? There's you've got no data there. What if we pump this up to 30? It's really starting to tighten our variance. This is cool. This is very, very cool. I like it. Next, Bootstrap. Also, big fan of Bootstrap. So much of frequent testing theory in centers of good estimators. The precise distribution of these estimators, however, can be often difficult to drive analytically. Yeah, sometimes you just don't know where the data came from, right? So the computational technique known as Bootstrap provides a convenient way to estimate properties of an estimator via resampling. All right, what does this mean? I like to think of it, you get all of your observations, you put them in your little bag, and then you just put your hand in it and just draw on and just keep drawing it with replacements. So you draw it, look at it, and say that's my sample, and then put it back in the bag, right? And you keep doing that at time and time again. That's really all bootstrapping is. Reason is some things just can't be modeled, especially in finance, especially with things like Bitcoin, where there's just no distribution that's going to be able to model it. There's no parametric distribution. So what can you do? I think bootstrapping is probably the only way. There's just because the numbers are so wild that they're going to be meaningless. Things like 15 standard deviation moves. Well, nonsense. Anyway, let's have a quick look. Obviously, let's go for normal. Makes life easier. All right, so that's our distribution. Choose a sample and resampling size and sample from the chosen distribution. So 10. I'm going to choose 10 random numbers from this. Obviously, it's going to be most likely to pick around the mu. So I'm going to pick those 10. Okay, so that's my bootstrap. So what if I do resample? Essentially, I'm randomly picking from those 10 numbers, and the average came out as that. So what if I resample 100 times? Trying to estimate the error of the mean. So sample from that, sample 100 times, and I start to get a distribution around that mean. Pretty cool. Love it. Next, Bayesian inference. All right, this is like right up my alley. I'm a Bayesian. Got my Bayesian tattoo. Actually, no, that'd be a great one. Bayes theorem. All right, Bayes theorem. Disease. Okay. Make it COVID appropriate. Suppose that on your most recent visit to the doctor's office, as you do, you decide to get tested for a rare disease. If you are unlucky enough to receive a positive result, the logical next question is, given the test result, what is the probability that I actually have this disease? I mean, that's a very valid point. Because, tests are, after all, not perfect, and this disease is very rare. So those two have to be taken into consideration, right? So Bayes' theorem tells us exactly how to compute this. So probability of having, so this is read as follows: probability of having the disease, and this little bar means given. So given that this second event has happened, plus I'm going to assume is going to become a positive result from the test. So what's the probability of me having the disease given that I have a positive result, right? So we actually break it down, and this is just essentially Bayes' theorem, and it says it's actually probability of getting a positive result given you have the disease. So most of the time when you get like a pregnancy test, most of these examples done on pregnancy, I guess they want to do it a bit more pandemic special. But it's like, this test is 99% accurate, whatever. It's usually this value here. So probability that the test is positive given you have a disease. That's really what you care about. I care, look, I've actually got it. So disease has happened. You have the disease. I do the test. How accurate is the test? It's this value here, right? So most of the time, just say it's 95% accurate or whatever. Plus, you actually got to multiply the probability of having the disease. So this value here typically is very small. It's a rare disease, right? So you're actually shrinking that down massively. But you also need to see what the probability, if you want to sort of standardize it, probability of getting a positive result regardless, right? So as the question indicates, the posterior probability of having the disease, given that the test was positive, depends on the prior probability of disease, P disease. Think of this as the incidence of the disease in a general population, right? The set probability by dragging the bars below. So healthy, 90%, disease is actually 10%. So it's not that rare, right? So what do we do? The posterior probability also depends on the test accuracy. How often does the test correctly report a negative result for a healthy patient, right? So that's really what you care about. False positives and the like. And how often does it report a positive result for someone with the disease? Determine this two distribution of all. So this essentially probability of negative given you healthy, probability of positive given you're healthy, probability of a negative test given you got the disease. I mean, obviously these are massive numbers. I think this is just to sort of prove a point, obviously, right? So test one patient. Let's try. If I test one patient from the population, okay, so this is my population. They're actually jiggling about a little bit, especially when I jam them. They sort of shuffle. I love it. So there's a few people with a disease, and that's probably this 10%. So if I just jam it all the way up, everyone's red, everyone's got the disease. What if I just make it 99? There should be eventually just a couple of people which are healthy. Actually, let's have a nice clean world. There's only very few people which are walking around in red with the disease, right? And then obviously we can actually play around with our test results. So we want our test to be very accurate, and we care about these two. We want to make sure that that's what makes a good test, is these two numbers being high, right? So if we test the patient, he was blue, he doesn't have a disease, should ideally, in 90% of the times, actually come out with the correct result. If I test the remaining, I test the whole population. These are my negatives, these are my positives. So this is my false positive. This guy here, this guy in red, he came out with, we said it was negative, he didn't have the disease, but he's red, he actually does have it. So, I mean, that's your inaccuracy in test. Here, positive, it's a big fat mess, broadly sort of 50-50, not a very sort of good test. Also, if I jam that up, make it everyone should be sorted correctly if I do this, right? Blues to the left, reds on the right, as you expect, right? This is an ideal world. Everyone that does the test gets exactly what they should have. Amazing. This is cool. This is really, really nice. Big fan of this. And then we can compute this table based on the above. Love it. All right, likelihood function. So here we got these. Let's go for statistic. Likelihood function is a very precise definition. Concept of likelihood plays a fundamental role in both Bayesian and frequentist statistics. The probability of observing that data given these parameters. So what's the likelihood of these parameters? So on the left, you've got the likelihood. So what's the probability that these parameters were generated from this data? And then we sort of flip it. Probability that this data was generated by these parameters. Choose a sample size n, sample once. So I'm going to sample a value. So that's my density. Use the purple slider to, that's going to be my likelihood. So it's very likely, if I pick that here, my likelihood is at its highest point. So that's really when you hear terms like maximum likelihood, where you're just trying to optimize that value there, rather than saying, okay, well, it's actually likely that the parameter, theta, is sort of sitting here. Well, actually, it should be sitting there. That's why it's at its maximum. What if we do loads? Sample loads. Okay, that's my density. Where does my maximum likelihood sit? That's like my average. Beautiful. Now this is really nice. That's my likelihood function. So essentially we want to maximize it around there. Amazing. Prior to posterior. All right. The core of Bayesian statistics is the idea that prior beliefs, so prior is essentially information you do before the test even happens, should be updated as new data is acquired. Consider a possible bias coin that comes up with heads probability P. Purple slider determines the value of P, which should be unknown in practice, right? You don't really know what that is. Pink sliders control the shape of the initial beta prior distribution. Let's have a look. Let's flip the coin 10 times. What does that look like? So we should approach that value there. This P should change I'm actually making a bias, right? And what is this distribution here? It's my prior. What I think is probably more likely to sit one way or another. So there's a whole world of priors that you can really pick to try and really just shift like the weight of where you think the parameters should sort of be. If I flip it, it's actually not bad, you know. It does get there in the end. That's actually pretty cool. Really nice. I think there could be better examples than this, but overall, you know, pretty nice. All right, quick one. I know this is it's a long video. I'll make it really quick. I think Is there something else after this? Regression, last one. Obviously, we finish on regression. The most advanced topic in statistics is clearly regression. OLS. Everyone needs a little bit of OLS. All right. OLS, ordinary least squares approach to regression, allows us to estimate the parameters of a linear model, right? So it's just a straight line through some data. The goal in this method is to determine the linear model that minimizes the sum of squared errors. So we have this penalty term, which is essentially we've got a line of best fit, and any deviation from that line, you get penalized twice as much, squared, as the distance, right? So we create these sort of squares around the data. Explore the OLS model through the 4 infamous data sets. Infamous in the Anscombe quartet. Never heard of it. Choose one of the number 1. All right. Got some data, X and Y. Looks like I got a regression line and some values here, N, 11, so 11 observations. X bar is going to be my mean of X. Y bar is my mean of Y, 7.5. So beta 0 is the intercept, 3, so that's where that sits, and beta 1 is your slope. Okay, can I do anything? 4. Oh, so that's the regression point. That's the actual observation. I can move the observation, and that changes the weighting. So this square is what it's trying to minimize, and it's trying its damn hardest to make sure that this line... that line makes that square as small as possible, all right? But I can just do something silly, like maybe like a smile. Bring that down, you know? So you've got points which, and this is obviously where OLS sort of breaks down, right? Because you've got most of the data sitting down here, a couple of points up here, these outliers if you must, and they're saying, well, actually the line's sort of completely flat. Let's sort of try and adjust that a little bit. Make that beta 1, let's make it 0. There we go. All right, so all this data sits down here, 2 points up there, completely flat. Obviously, your SSE, your sum of standard error is massive. Essentially, I guess it's the sum of all these squares, right? So it's huge, huge, huge. I can make that smaller, put it on the straight line. That SSE should shrink. This is awesome. Different data sets. Let's have a look. Oh, yeah. So that's clearly very non-linear. You can probably transform the data, and that's probably what I would do. This one here. Okay, you've got that outlier. And number 4, everything's sitting on top of each other. So you can't really sort of regress it. There's nothing really there to do. Very, very cool. Correlation. All right. I guess another super misused tool in stats. Correlation is a measure of the linear relationship between 2 variables. I guess that's really what it is. It's trying to fit a straight line between things. Defined as a sample of the following and takes values between plus and minus 1 inclusive. Cool. Yeah, pretty straightforward. All right, these are all the definition. It's like, you know, deviation from the mean squared. All right, and the can also be understood as the cosine of the angle formed by the OLS line determined in both variable dimensions. And this I don't know. Setosa. All right, I got Setosa. All right, so I've got a correlation matrix here of Setosa, length, width. Let's pick 74. So you're telling me that I regress these 2 against each other, and the line that is formed, the cosine of the angle, is 0.74. Wow. All right, if I had to take one takeaway from this, like, I have never heard of this. This is amazing. How something visual like this, and, you know, we put in regression, and we're putting, like, I'm sure there's a very nice proof somewhere of why that is so, but let's look at something else. 18. Do a calculator, trigonometry. All right. I mean, let's. Look, I'm not a natural. I don't have cosine in my head, right? So what's that? Let's call that 70 degrees. So if I go 70 cosine, all right, maybe not. 34. So maybe let's pick something else a little bit easier. Okay. I'm doing something wrong, which has happened before, which is fine. You know, haters, trolls in the comments, boost my video. Look, awesome. If that's something I didn't know, and I'll look more into that, but that's really cool. Analysis of variance, ANOVA. This just takes me back. Don't really do this much in real life. Well, I don't anyway. Testing whether groups of data have the same mean. Let's have a data. We all love a bit of iris data set. Can't change what's going on. I guess there's like an F probability, treatment error total. Drag and drop data points and explore how this affects. So I can actually change this and this, essentially saying, oh yeah, do the p-value, it's done by the F statistics. F stat, yeah. Mean squared error, degrees of freedom, sum of squared errors. Essentially each of these has a sum of squared errors. Each of them. And then we have a p-value of rejecting it. The same mean. Well, I would say, no, if I drag this up, these are clearly not the same mean, so I guess that is rejected. Cool. Home. Look, that was awesome. Chapters about, there's a book. Really cool. Long video, sorry. I just got lost in the visuals. I really love this visual stuff where you can interact, and there's obviously hugely popular channels which we aspire to. 3 Blue 1 Brown. They're sort of taking it to the next level. You look at the view counts and you go, look, you're clearly appealing to an audience far bigger than just us geeks that do this on a day in, day out basis. The concepts are simple to understand when people can see them visually. I think this is a great start. Obviously could be better, but I love to be able to do more things like this for my channel and make things that are interactive for people that maybe don't want to code, they just want to drag and drop and do something like this. Love to hear your thoughts. What do you think of websites like this where people obviously clearly put many months of work into making them happen? If you'd like to see more things like this from me, maybe on dirtyquant.com, which I'd love for you to go and register and sign up and have a chat. But if I made that website obviously more interactive rather than just the typical Python notebooks, which I do. All right, catch you on the next one. Cheers. Bye.